Today's speaker is Professor Khabat Heshami. Khabat did his PhD at the University of Calgary, Canada, under the supervision of Professor Christoph Simon. Khabat graduated in 2013 with a thesis titled Toward Practical Solid-State-Based Quantum Memories. He then held a postdoctoral position at the Institute for Quantum Science and Technology in Calgary. In 2014, Khabat joined the National Research Council of Canada. He is now a research officer and leads several of the NRC's quantum optics projects. Since 2018, Khabat is also a professor at the University of Ottawa. Khabat is a world-leading expert on quantum optics. His work spans both foundational topics such as superpositions of causal orders and practical topics such as optical quantum metrology. And today, Professor Khabat Heshami will be telling us about the latest news from the quantum communication endeavor. So with these words, Khabat, thank you very much for joining us, and the virtual floor is yours.
Thank you, David, for the very kind introduction. I'm going to start sharing my screen and then, thank you very much, David, for the kind introduction. It's a pleasure to be able to speak today. So I wish this was in person. We could sort of interact more directly, but please feel free to stop me at any point. I would like to take questions as we go. We don't have to wait till the end of the seminar. So today the title is Quantum Communication, and I'll talk about a few things. That's why it's called From Laboratory Scale to Global Distances. So obviously addressing sort of quantum communication over global distances is yet not within reach, but that part we'll talk about ideas. And we have sort of theory and experimental results and sort of over small distances, which is achievable at the moment. So I'll talk about those two directions, but I'll be more specific as we go forward. First, I'd like to introduce the group. So we call ourselves Photonic Quantum Information Processing Group. This is our building in Ottawa. That's the National Research Council. It's a national laboratory in Canada with sort of many areas to cover, but we are a group inside the theory and computation group in this building. And we always interact closely with our experimental friends. So the theory portion of the group is smaller, but we have friendly experimental colleagues joining us all the time. As David mentioned, we have a few other areas to cover. We have a broad range of interest, but today we'll talk about some recent results that, or build up to some recent results that we had in the quantum communication area. This is the cartoon that I like to show always. It's a map of Canada. It's a big country, so it won't be trivial to do quantum communication over thousands of kilometers. This is this cartoon is trying to represent that challenge. The idea is that it will, if we want to go to those type of distances, it will require satellite communication, and also for shorter range of distances, it will require sort of fiber-based connections. And there are more sort of elaborate ways to also communicate on the ground, such as quantum repeaters. And so I'd like to highlight these papers, for, all of them trying to provide an overview of what is known as the quantum Ethernet or quantum network as an emerging topic. What do we need for quantum communication? For quantum key distribution, a single photon source would be sufficient. Alice will send a photon to Bob and try to encode information. You could do the same experiment if you have a photon pair source and source of entanglement, for example. But the challenge is distance. So if you think about sending photons down a fiber and assume 0.15 dB per kilometer loss, and try to go to a distance of 2,000 kilometers. Assuming that you have a source that works at the rate of 1 gigahertz, then that's a relatively generous assumption. The sources are getting there, but it's a generous assumption. It'll take more than the age of the universe to send one photon across the 2,000 kilometer distance. So clearly this is not practical if you want to communicate over that type of distances. So we have to come up with other ways. In terms of just direct transmission, not doing anything sort of elaborate, then we either rely on sort of ground-based links through telecommunication fiber. It can be practical up to 500 kilometers. It depends on the type of rates that one would aim for. Then if the application in mind is only quantum key distribution, which is sort of sharing a random sequence, then one could sort of resort to the approach called trusted nodes. And if you're not familiar with this term, it means that I'll send my photons over a few hundred kilometers, measure them, turn that into the random sequence that would be my secure key to be used later. But when it's turned into these sort of classical bits, it's not secure anymore to transmit that out over another link. But you can have another link establishing a similar key and do kind of an XOR operation. But what the trusted node means is that you have to trust the building and the operation at those points when you turn the quantum state into a classical bit, because then the quantumness is not going to help you to provide security. So this approach has implementations at least in a couple of places in the world. Like China has, I think, a trusted node network over 2,000 kilometers, if I'm not wrong. So clearly that's not direct fiber transmission. It's going from one station to the other and measuring the quantum state, turning it into a classical bit, and then sort of a random string of bits, and then trust that location to hold that secure for you. Then if we give up on fiber-based links, then we can switch to low Earth orbit satellites. You can look at sort of link losses for satellites, and it roughly allows you between 1,000 to 5,000 kilometers, depending on where the satellite is and so on. And if you go to geostationary satellites or middle Earth orbit satellites, then that's the distance range is 5,000 to 14,000. But these are not sort of set in stone. It's just rough estimates, and again, depending on what type of rates you would like to aim for. So clearly, this is limited. What if we want to cover, let's say, other range of distances, which would be necessary if we want to go have a quantum network over long distances? So here's sort of the more elaborate ideas that I mentioned. So ground-based repeaters, this would be a collection of shorter links, which allows us to do entanglement generation. So we generate entanglement over smaller distances, and then do entanglement swapping to be able to connect these smaller links and go to a long distance. So this is more powerful than quantum key distribution because it allows you to establish sort of entanglement over a long distance, but it can be used, that entanglement can be used for quantum key distribution as well. So there are estimates that you can use the system to cover 500 to 1,000 kilometers, but again, a lot of assumptions goes into this in terms of what type of memory efficiencies you can get, what type of source rates, and what type of multiplexing rates you can get. So that's one approach. And then there's another approach to quantum repeaters that doesn't require quantum memories. And this fully relies on a quantum error correction to compensate for loss, for an entanglement purification down the road. So every step of this approach is so dependent on the ability to do quantum error correction. And the limitation that it has is that it cannot tolerate more than 50% loss. So it means that you need a lot more nodes along the way to cover a long distance. But if you look at this paper, it showed that you can reasonably cover these range of states, range of distances of about 1,000 to 5,000 kilometers. The problem is it's demanding in terms of the type of sources it requires. This protocol in particular requires a source of cluster states, let's say, 15 photon cluster state, for example, in a particular arrangement. So that's not something we have at the moment, but different groups around the world are taking steps in that direction. And then this is something that I will talk about. This is something we proposed, is that if you have low Earth orbit satellites to establish links on the ground, and then store those the entanglement in quantum memories. So then the rest on the ground would be a standard quantum repeater, similar to what's mentioned here. That, because then you don't rely on the fiber link on the ground, you can go, each individual link could be much longer. And then we showed that you can go to 5,000 to 20,000 kilometers, and 20,000 is sufficient to go around the globe. So those are the range of things that is required to be able to do quantum communication across a broad range of distances. The other thing I just mentioned as a side note is that some systems show coherence times in the order of hours, and you can see this here. This was done in the rare earth nuclear spins of rare earth doped crystals. Then one can imagine if I can load enough number of qubits and store them into such a quantum memory, if I have enough time, I can put this on a flight, and in 6 hours I can reach thousands of kilometers. So that it's probably a very expensive way of transferring qubits, but when the coherence times are this long, it could become a possibility. Okay, so you might ask, why do you want to share entanglement over long distances, or send quantum states over such a distances? There are a range of things that I can talk about. So obviously QKD, quantum key distribution for secure communication, that's the most studied and obvious case of for an application. But then, I encourage you, if you're interested, to look into this paper, which is different ways of doing private quantum computing. That means private means different things. You either try to, for example, you have a server that holds quantum computing power, and you want to send your problem to be solved on the quantum computer, but you don't want the server to know about the problem you asked and the solution that it finds. So there are different ways of imagining security for the question that you're asking and the answer you're collecting. It's a rich topic, but one of the scenarios described in this paper is that if your quantum computers, if you separate your computation over 2 quantum computers with space-like separation, then you can come up with ways to make sure that the company providing the quantum computing service have no way of finding about the problem and the solution that you're finding for the problem that you're posting on this quantum computer. Obviously, we're far from sort of these capabilities, but it's an interesting area to look into. There are other ideas, such as private query. This would be searching without letting the database holder to know what you're searching for. There are other ideas. For example, you can increase the baseline of telescopes by sharing entanglement between them. So instead of doing individual measurements at 2 telescopes, you do sort of interferometric measurement between them. This allows you to, in principle, sort of increase the baseline of your telescope. Again, for that, you can look at ideas in this paper. And there's a whole list of ideas like fundamental tests and this review paper, a relatively long review paper you can look at, and what sort of it tells you about sort of things you can do with entanglement over long distances. The other idea would be having a network of clocks. So at the moment, we have very precise atomic clocks to the point that, for example, if a clock is on a different optical table, experiencing slightly different amount of gravity, it will show you a different rate of time passing. Then and then we still don't have really experiments that would allow us to have have a global clock, let's say, that would give us measurement of time over over distances. And this paper came up with this idea of, if we manage to entangle clocks, what type of advantages one could extract from that. And obviously, in the end, it's distributed quantum computing. This doesn't necessarily could be done in a room, so it doesn't necessarily require communication over long distances unless you want to do private quantum computing. But there was this paper that came out last week, and they looked at not only interconnecting quantum computing devices would be a nice way to approach scalability, and then this paper showed that you can even get better fault tolerance if you take this approach. So obviously, a lot of interesting areas to look into in terms of what it means to share entanglement over different devices. Now I'd like to focus on the quantum key distribution, but then later I'll come to the quantum repeater side. So this was originally introduced in 1984 by Bennett and Brassard. Their protocol is well known, and it's still one of the most efficient ways to do quantum key distribution, depending on the conditions. But it's one of the best ways to do quantum communication, or quantum key distribution specifically. The idea is that, if you're not familiar with this idea, I'll go through it step by step. So Alice randomly chooses a basis. We can think about polarization of the photons in this case. It's easy to take that approach. So you either choose horizontal, vertical as a basis for encoding information in the photons, or diagonal, anti-diagonal. So both of these are valid choices for encoding zeros and ones in the polarization of photon. Then, if she wants to send a 0, she chooses a horizontal, and for a 1, she chooses a vertical. If the basis is horizontal, vertical, and the same approach, diagonal, anti-diagonal, and that carries information about the bits that she's trying to send. Then transmits that to Bob. Bob again randomly chooses a basis to measure. The basis is either diagonal, anti-diagonal, as a diagonal, anti-diagonal, or horizontal, vertical. And then from that measurement, Bob will extract results and starts to interpret those results as zeros and ones, depending on the measurement outcome in each basis. And this is repeated many times. So how this would look like in the end, this would be the result. For each attempt, Alice has a basis and something that she chose to encode, 0 or 1. And then, so when this is done, the sequence is created. They pick up the phone, they start communicate over a public channel that Eve, in principle, anyone can have access to. And they compare, they don't discuss the results, but they compare the bases. So that means some of the, so well, first they identify the photons that didn't arrive. That's just loss. So we take those out. Then they identify those that they chose the opposite basis. So in this case, for example, Alice chose horizontal vertical, and Bob, for the measurement, chose the diagonal anti-diagonal basis. And this will result in a random outcome. So no correlation between what was encoded and what will be extracted. So they will just, they compare their bases, they throw out those cases. But between what it's left, you can see that if the basis for the state generation, the measurement was the same, they most likely will extract the same result unless there's someone is interfering with the channel. So yeah, and then translate those into zeros and ones. That becomes your sequence. Because the system is not ideal, some of these will end up carrying sort of errors. So for example, well, this one I should have removed. So I'm not showing any errors here, but if there is an error, there are steps like privacy amplification. So they first have to sort of reveal part of the sequence. They compare and have an estimate for the error. And depending on the amount of error, they can trust the channel or they cannot. And then they sort of take the next step based on the estimation of the amount of error in the channel.
Sorry to interrupt you, Khabat. I have a question here from an anonymous attendee. They're asking, what do you do about dark counts? That is, maybe your photon disappears and is lost, but some dark count triggers Bob's detector.
Exactly. Yeah. So that's also noise. That's error. You might. So, for example, in this case, where they had the same basis, but the photon was lost, but my detector might still fire and give either the diagonal or an anti-diagonal photon. So I might detect a diagonal or anti-diagonal photon with completely random because it's coming from a detector misfiring. That will, when they select a subset of this string of zeros and ones and publicly share it, that's not the part that they will use as secure key. That's just the part that they will use to estimate the amount of error in the communication. That will pop up as an error. And if that error is higher than a certain threshold, then they just throw away the entire string of bits that they generated. If it's lower than a certain amount of error, and then they can do privacy amplification to remove those errors from their bit string. And I'll mention what that threshold is in the next slide. I hope I answered the question.
I think that's clear. Thank you.
So the threshold I mentioned for BB84 in dimension 2, it's 11%, and that's the point where up to that amount of error in the bit string, you can tolerate that amount. You can prove mathematically that your link is still secure up to that threshold. Beyond that, the key rate, the secure key rate or the secret key rate goes to 0 or negative, which is not meaningful. But any amount of error below 11% is tolerable, and it results in a non-zero secret key rate. Now, one thing that we're interested in is that, can I encode more information? Obviously, in polarization I cannot. It's limited in terms of degree of freedom, but I can have I can use other degrees of freedom of a photon to encode information, and that in principle would enable me to do this same protocol in a higher dimension. So instead of encoding 0 and 1, I can encode 0, 1, 2, 3, and that would be a 4-dimensional BB84 protocol. And people now already know the secure key rate, for example, how it behaves, and how much error that protocol can tolerate. And you can keep going, actually. You can even try to increase the size of your Hilbert space and the encoding, such that you can go to very high dimensions. And this is how the secret key rate behaves as a function of error and as a function of dimensionality here. So at 0 error, you can have so four bits of information if you're using a sort of a 16-dimensional quantum state. And this BB84 and a high-dimensional BB84 protocol. So there is some benefit to go to higher dimensions when, for example, you want to tolerate more noise, and there are different scenarios, for example, that could be the case. So that's how this particular protocol behaves as a function of dimensionality. So there are different ways I mentioned to encode information. While polarization is one, but it's limited in terms of dimensionality. I can just take a broadband pulse, look at different colors, and try to, encode information in the frequency domain. And also I can just pulse shape my photon such that I have different time bins, and then there's no limitation. I can go to any dimension if I encode in time. Then one thing that our experimental colleagues were interested in, and they're expert in creating, measuring these, and manipulating these states, is the orbital angular momentum state. So the spatial structure of the light. This is the intensity and phase profile of these orbital angular momentum states that we used in an experiment for these type of quantum communication exercises. So what do you need in general? You need a photon source.
Sorry to interrupt you again, Khabat. And you might be, maybe you're just about to say this, but we have a question, and it is, how do you change the angular momentum features and shape of a photon?
I'll mention it briefly, but I can say it now. For example, like spatial light modulators is one way. They're not fast in terms of if you want to quickly change between different states, but the main tool being used by our colleagues is a spatial light modulator. So it's that's how you can start with a Gaussian state, so it has no spatial structure, and you can add spatial structure to it with an SLM.
And then I have, thanks for that, Khabat. And then I have another question from our PhD student, Jed. He's asking, is it possible to just use 2 qubits as one qubit to make the protocol more error tolerant? That is, use 0, 0, 0, 1, 1, 0, and 1, 1 as the state 1, 2, 1, 0, 1, 2, 3 of a 4-dit.
Yeah, no, I unfortunately I removed that slide. But if you reach out to me, I have a paper to share with you. There's a Physical Review Letters paper by Markus Huber, who explicitly shows that you can't necessarily recreate the high dimensional state by just bundling more qubits. So there are particular states in the high dimension that you cannot reach with, and there are more subtleties to this argument. In certain cases you can, but not in general. So if you reach out to me later, I can share the reference with you.
Okay, thanks.
So first we need a source. It could be various approaches to creating photons, and then encoding, polarization, time band frequency, the continuous variable domain, and the spatial modes, as we talked about. And you need, well, channel. That's our experimental colleagues. They looked into all three of these. We did underwater, free space, and fiber-based communication. This is just the medium that you send your photons through, and you need some detection idea, and it gets complicated when you deal with these orbital angular momentum states. But all of this, you have to come up with a protocol that would guarantee and provide you a way to show, to prove that your protocol is secure as well. So the protocol guides the mathematical proof behind the security as well. One thing my experimental colleague, Fred Bouchard, did was he came up with an experimental setup, as I mentioned, based on these SLMs, that it wasn't doing one particular protocol. He could use the same setup, fix the setup, not change it, but change the protocol such that you can sort of directly and in one experimental platform compare all these QKD protocols. This was an interesting exercise. You can see there's a whole range of different amounts of theoretical and experimental errors. So theoretical error threshold you can tolerate, experimental errors that came from the experiment. You can see BB84 in different dimensions, 2, 4, and 8. And these are other protocols that I won't have time to go into, but this is one experimental paper that you can look at, which addresses several quantum key distribution protocols in the same experiment. One quantum key distribution protocol I like to highlight is it's called round-robin differential phase shift QKD. This was initially introduced in this paper in 2014 as a way of doing quantum communication without monitoring error. As you remember, you might remember that I mentioned that you have to look at the results. So Alice and Bob in BB84, they have to compare their results so that they have an estimate how much error is in their bit string in the end. This protocol came up with a way that remove that requirement, so you can still do secure communication by without really even looking at the amount of error in the channel. The reason the way that this was achieved was that they started encoding information in this high-dimensional Hilbert space, but they only encoded bits of information in the phase difference between different modes. So let's say if you encode in time, you get this sort of pulse chain coming out, and the phase difference between each, for example, between mode 1 and 2, that's a phase difference of pi. I will call that a bit of 1. And then between mode 1 and 3, that's a phase difference of 0, and I'll call that a bit 0. So no surprises up to here, but they showed that Bob can use this variable delay that is randomly selected. So with an interferometric measurement, so anyone interfering with the channel wouldn't know that which two modes Bob would select to look at the phase difference. And that in itself put a bound on the amount of mutual information between Alice and Eve, or Eve would be anyone interfering with the state in the middle. So that upper bound, independent of anything else, just dependent on the dimensionality of the encoding, the dimensionality of the Hilbert space you use, that was the key to be able to do quantum key distribution without monitoring the noise. So this was an interesting idea. Then several experiments came out, and we did our own experiment, again using, well, I'll mention that in a moment, but just to put some mathematics behind what I described is, this is what's describing the state that Alice creates. So you put a single photon in many modes, L modes in this case, and you encode information in the phase differences between the modes. Or you can randomly put phases on each mode, and then the phase difference becomes random. And these SK values are just zeros and ones. That's what's going to translate into a secure key. What Bob does is that randomly selects a mode K and then a shifted mode by a mode that's shifted by R. and then look at the phase difference between mode K and K plus R. And that's this interferometric measurement that you see down here. As I mentioned, the amount of information that this state can share about the key being measured here with someone staying in the middle is always bounded. And that bound is, this is just the average number of photons in the pulse train. And if you keep that to a single photon, it's just purely given by the L being the number of modes that you're using to communicate between Alice and Bob. So this was interesting as an example. So like, for example, if L is 128, you use single photons. This, which would be the secure key rate, is still positive, which means that you're not reaching the threshold, even up to 35% error. So that's an interesting result. So a lot more error tolerance compared to BB84. So we did an experiment on this using the SLMs again, instead of using these interferometers, which is very hard to stabilize. The other experiments, they encoded in time. It's very hard to stabilize these things. But the SLM was a flexible way to do this experiment. Again, so this kind of motivated us to look at a different question, which was, as I described, was we had only 0 and pi, and that only allowed me to encode bits of information and not higher dimensions and carry more information in per attempt. So the question was, can I encode more information? Can I squeeze more information into the state and still remain secure with or without monitoring the error? That's the main question. So we tried to extend this protocol. So you can see we're using a similar state, but instead of the phases being limited to 0 and pi, now I'm encoding the phase in a higher dimension. D could be this is the dimension I'm choosing for my encoding. It could be 2. This recovers the original protocol, but it could be any number, so I can increase the dimensionality of my encoding. Then the measurement was not easy to figure out what type of measurement. So we came up with this extension, which is Bob, instead of shifting the state, will just randomly pick modes. So the D number of modes out of the L available. And then to measure those D modes, you'll try to measure them in a mutual unbiased basis. So the MUB is given by this formation, which is like a Fourier transform of the basis. It's one of the easily generated mutual unbiased basis states you can create in any dimension. So this this is the measurement. It sets the way that Bob will do the measurement. And then Bob communicates which subset that he selected, just the modes, not the result of the measurement. And then what we need to do just mathematically to prove, well, to find the secure key rate and then find these thresholds and see if this works, is that we assume that there is someone in the middle with a density matrix available and with a general unitary that would allow that person in the middle to correlate their state with the state that Alice generated and sent to Bob. And you let that unitary to be anything possible. And then we try to find bounds on the mutual information that unitary creates between Alice and Eve, or the person that was trying to copy the state or extract information from the state. And that type of attack is called like a collective attack. It allows, so that general unitary allows that the person in the middle to extract some information from the state going through. But through some lengthy calculations, which will soon appear, hopefully next week, you can find what is the upper bound on the mutual information between Alice and Eve, and that sets the amount of secure key rate that you can generate between Alice and Bob, or sets a limit on it. These are some results that like to mention. So we looked at the error threshold as a function of, so this is for different L. L determines the size, the number of modes you have, so the size of the Hilbert space. D is the size of the encoding, so you choose to encode either just 0 or 1 or a higher dimension. So these are different encodings, and it shows that how the error threshold changes as a function of L. The upper plot is for the case where you're not monitoring the signal the disturbance or the noise in the channel, and part B is, or this lower plot is when you do look at the noise in the channel, because then now you have more information about the amount of error in the channel. And here it's the same plot, assuming that there's no error in the channel. This tells you what type of rates you'd get as a function of dimension and L, dimension of the encoding and dimension of the Hilbert space, without for the top and with looking at the channel. Because when you look at the channel, it gives you some information about these parameters. It puts a bound on these parameters. So it allows us to put a tighter bound on the mutual information between Alice and Eve. So that's why we can extract more higher rates usually when you monitor the channel. Okay, I think this is the experimental setup. We were lucky to have experimental colleagues. They started doing the experiment. And these are the rate as a function of loss and distance that based on the experimental results. The main thing to characterize from the experiment is this misalignment error. If you're doing quantum optics, you're familiar with sort of interference experiments. This is directly related to the visibility of your interference, how well your interferometric measurement is performing in terms of visibility. So this is an extension of that notion to higher dimension, for example. And this is what they measured for different size of the Hilbert space and different dimensionality of the encoding. And that resulted in these sort of rate measurements here.
So there is a question here. I think maybe you mentioned it, but someone asked, what's the distance of transmission in this experiment?
This is in the lab. It's on one optical table. So there's no distance here. It's mainly used to measure the amount of error in the state generation and detection. Okay. So there's no error because of the channel, but then you can add loss and to this loss. And we had a question about dark count. So when you add those assumptions, then you can start calculating what would be the rate as a function of distance. And these sharp drop-off you see is directly because at a certain loss, the amount of photons going through becomes the same as the number of dark count photons you get from your detector. Then the rate quickly goes to 0. Those are why you get these sharp drop-offs in the rate. So that's how the distance or the loss goes into at least the calculation. This was not done in the experiment. In principle, you can add a lossy element that creates this amount of loss in the lab as well. But these are the theoretical rate calculations based on the experimental measurements.
Thank you.
How much time do I have?
So there is 15 minutes left.
Okay, including questions.
Including questions, but you're taking questions throughout. So I think you can leisurely, and if you run out over 1 or 2 minutes, we won't.
Okay.
We won't shut.
Yeah. So I don't have to. This is just another look at the performance of this protocol. I don't have to go into details here. So this is where the quantum communication discussion or the quantum key distribution discussion ends. I can take more questions, and then I'll talk about quantum repeaters, which allows me to do entanglement distribution. Any other questions?
There's nothing in the chat at the moment. We've answered everything that's come up.
We can always come back to it at the end.
Yeah.
So now the question is, there's always this sharp cutoff when you do quantum key distribution, for example. But that's when the amount of loss makes the number of photons comparable to the number of dark count photons in your detector, and then there's no way to increase the distance. That's usually called rate loss trade-off in quantum communication. There's one way to go beyond that limit, which is using quantum repeaters. And the way it's done, or the main ingredients for it, is first entanglement generation. What you do is that between point A and B, you create entanglement. We can talk about that how. So you do the same thing between C and D. And when you have both, you have confirmation that both links are carrying entanglement. Then you do entanglement distribution step, which is just an entanglement swapping operation between B and C. What that does is that it removes these nodes, creates entanglement between A and D, which is over a longer distance. The final step is that there are always errors, and the fidelity of this entanglement between A and D is not ideal. So what you can do is that you can have many copies, and then from the many copies, you can try to generate a higher fidelity copy using entanglement purification protocols. This was originally introduced in this paper, and then there's a whole body of work on this topic, but this review might be a nice way to read about quantum repeaters if you're interested. Another paper I would highlight is this work where they try to categorize different quantum repeater protocols based on where you use quantum error correction. So the one that I'll talk about is this first generation, which uses heralded entanglement generation for the entanglement part, and then also heralded entanglement purification for the entanglement purification step. So there's no use of error correction in this, in the simplest way of doing quantum repeaters. And the most advanced one, which is this third generation, is that you use quantum error correction to tolerate loss, also use quantum error correction to get rid of any operational error, which would result in a lower fidelity of entanglement. So everything would rely on quantum error correction, both from entanglement generation and to tolerate loss and to tolerate errors that results in lower fidelity. So that's an interesting categorization of the quantum repeaters. What I'll talk about is the first generation, where the entanglement is heralded, and the entanglement purification steps would also be heralded, so not relying on quantum error correction. What we try to estimate and see what it takes to go to very long distances, up to 20,000 kilometers. So obviously the fiber links are too lossy to do that type of operation. So we decided to take this out, replace it with a satellite that carries a source of entanglement. So you create an entanglement pair, send it down to the ground stations. And once you have a confirmation that the entanglement pair made it to the ground, then you recover the photons and do an entanglement swapping operation. That was the idea. Well, first we need to know what is the loss in each of these links or double links. This is a calculation was done by our collaborators at the University of Waterloo, and you can see different the different heights for the satellite and different ground distances results in different loss, double link loss values, but loss values of 40, 50, 60 dB are things that you can tolerate. So we can still work with these values. This is coming from an experiment from the source of entanglement on the satellite that China has, and it came out. This measurement came out in this paper in Science, where they showed that you can distribute entanglement over 1,200 kilometers using their source of entanglement on the satellite. So we extended this sort of calculation to even sort of higher satellites, including sort of middle Earth orbit and geostationary satellites, which will be quite far. Then
I have a question here about, I don't know if this is the best point to ask it, but the person asking the question says, it looks like you're considering standard bipartite Bell state entanglement.
Right.
Is there any benefit to using multipartite entanglement, like a GHZ state or a W state? And are there protocols that operate with such things?
I don't think I have a full answer for you for that question. There are particular states, like you mentioned GHZ. GHZ is very loss intolerant. If you lose one photon from a GHZ state, you lose everything. So I think it depends. For a W state, for example, is not that sensitive to loss. So it really depends on the type of state, but I don't have a deeper answer than what I just said. But it's a good question, and I have to think a bit more to see what are other scenarios and potential directions to think about.
I guess it's hard enough to do it with just Bell states. That
it is, yeah. But just fundamentally, I think it's an interesting question to think about.
And there is another question. Sorry to keep from Jed. He asks, how do we get past the no cloning theorem when repeating the signal?
So when you do entanglement, when you generate entanglement between two, so the no cloning, it tells me that I cannot make multiple copies of the state I have. For example, if I'm starting my entanglement source at A, keep half of it here and send the other half to Bob, that half is the one experiencing loss. So I cannot put an amplifier here in the middle to get rid of the loss. That's what the no cloning tells me. But it doesn't stop me from trying to get an entanglement created between A and B at a short link. So I make the link short enough that I don't need amplification here, which will make the state classical in principle. So I can still generate entanglement here. I can generate entanglement here. These two are both probabilistic. But if I have quantum memories at these nodes, and if I have heralding, it means that it's probabilistic, but when it's successful, I know that it happened. So I know that when this link is successfully created, I know when this one is successfully created, then I can do entanglement swapping to go any distance, to any distance that I like. And this doesn't suffer from the no cloning. I hope I answered the question. I'm not sure if that was the point that Jed was asking about.
I think that's clear. Yeah. Thank you.
So we looked into the scenario. One thing is that you don't have heralding when your source is here in the middle. There are other ways to have heralding entanglement generation. What you need is that you need a non-demolition detection of photons on the ground. That's hard, but we had an idea how to do it, and that's discussed in a separate paper. But anyway, this composition, which means that I have a photon source and satellite, non-demolition detection that gives me a signal for the arrival of the photon on the ground, and then followed by the storage of that photon in a quantum memory. It allows me to create these links on the ground. And then when the links are successful over this basic L0 distance, then I can recover the photons from the quantum memory to do Bell state measurement. And then you put all these things together. Each of these are probabilistic, have certain efficiencies, and so on. You take all of that into account. You consider parameters for your satellite. This is what we get in terms of rates. So we can show that we can go up to 20,000 kilometers. I'm not going to go through the comparison here. Just that there's one more topic I'd like to get to in the next couple of minutes. So I mentioned, so the heralding entanglement, there are different ways to do it. I mentioned that, for example, you can have a photon pair source close to one of the nodes, store that photon in a quantum memory, send the other one to the other quantum memory. But you could also have a heralded way to do this. So it means that you put another source here that it's guaranteed that both photons will make it to the quantum memory, and then the other half will be combined in the middle to do a Bell state measurement. And that's sort of a two photon measurement that would guarantee creating an entanglement between the quantum memories. Once that's created and you have a heralding signal that's done, then you have your link, and then you do the Bell state measurement again between the quantum memories to create the longer link. So that's how, so at least quantum repeaters with quantum memory linear optics is done. There's another way. Instead of two photon entanglement, you can rely on single photon entanglement. That's a scenario we considered in this paper fairly recently. The main idea in this paper was that can we do this without cryogenics? So quantum memories have to be at room temperature. Photon sources typically they are at room temperature. You don't need cooling. And the other thing to consider was that our detectors had to be at room temperature, or at least not cryogenically cooled. So thermoelectrically cooled was okay. This is mainly if you want to do this with thousands or millions of components. If you rely on cooling, it will become very expensive. That's why we're looking at ideas to see if we can do this without cryogenics. And the answer was yes, but the results are not better than the sort of the ideal scenario, obviously, because you allow more errors, for example, from your detectors, and also the quantum memory part can become complicated when you don't allow cooling. So the scenario we had in mind was it's a gas mixture when you have sort of alkali atoms and you have a noble gas, which this is used for the long storage because the spin state of noble gas, unfortunately, it's not directly addressable, so you can't use it directly as a quantum memory, but you can mix it with the alkali atoms where we know we can use this sort of lambda level structure to do a quantum storage in the spin state of an alkali atom. But then if it's mixed with certain parameters with the noble gas, I can, just through the collision exchange, I can map this coherence onto the nuclear spin of the noble gas, which will stay coherent for a long time. So this would be my main, this is transferring information, let's say, from a photon into an electronic spin state of the alkali atom. It doesn't stay for long in terms of coherence. So to keep it coherent over a longer time, I rely on the collision-based exchange to go to the nuclear spin of the noble gas atom, which will stay coherent for a long time. So that's the idea. There are other thoughts that go into it. For example, we need to get rid of four-wave mixing and other sources of noise through in this process, which is present, and also try to make this photon to spin and then spin to spin as efficient as possible. These are the results. We show that these are the rates you can, or the distances you can reach with the system. Well, but a lot of parameters go into it. So there's, I'll just encourage you to go and look at the paper. As I mentioned, forward mixing noise, you have to deal with it. It's important. You have to engineer the density of atoms such that the memory efficiency is high, your spin exchange rate is high enough so that you can transfer the coherence to the noble gas. And rate of single photon sources, you have to have a high rate photon source. And the detectors without cryogenics, that's the part that is also important. This is a developing area, so some people are trying to make these detectors better and better at room temperature, and but we try to include the state-of-the-art numbers in our estimation to see. The main thing that our protocol suffers from is the dark count rate, which a dark count from the detector, as it came up earlier, can give me a false positive from my from the single photon detection that I'm relying on to establish the entanglement between the two quantum memories. So a fake click at these detectors could give me that could quickly lower the fidelity of the entanglement generation. Okay, yeah, so for that topic, I'll just encourage you to look into this. With that, I'd like to finish the talk and just thank you for your attention, and also highlight our collaborators. And so from the round robin theory and experiment, these three colleagues were involved. From the quantum repeater without cryogenics, this was a collaboration with a group of Christoph Simon. And the experiment on the round robin experiment, that round robin quantum key distribution, was mainly done by the group of Professor Karimi at the University of Ottawa. With that, I'll thank you and take questions. Thank you.
Thank you, Khabat, for a very nice talk. I can see we have one question in the chat for now. If anyone else has questions, please just write them, but I'll read this one out. So Haumo asks, I'm curious what the sacrifice/drawbacks of encoding more dimensions and transferring it. Will it slow the transmission speed, or will the rate of information transmission?
So I'll have one number to show just to make a point. In an ideal world, you would like to just keep increasing the dimensionality, because if there's no error, you just keep gaining in terms of the amount of number of bits per attempt, or that you can achieve. The problem is, you can see that we did that for BB84. Dimensionality was 2, 4, and 8. And after sifting, I think you can see that dimension 4 had the highest rate. The reason is that when you go to dimension 8, then the error, the experimental error, doesn't stay fixed. It just keeps increasing. The one way to think about it, for example, is that when you try to do an experiment in a higher dimension, for polarization, you only need 2 detectors. So you only open 2 detectors at one particular point in time to collect photons. If you're going to these higher dimensions, it means that you need more detectors to be ready at a certain point in time. And those detectors could give you more dark counts, resulting in error. So the error doesn't stay constant as you are increasing the dimensionality of the encoding. That's the main problem. In this particular experiment, we noticed that dimension 4 was actually optimal in terms of the rate, the experimental rate. The theoretical can always go higher in an ideal world.
Okay, so if there are other questions, please put them in the Q&A section. I have one question from the chat. So someone says, a couple of years ago, I went to a conference, and on the session for quantum communication, everyone talked about something called device-free or device-independent quantum cryptography. Is this still something that people care about? And can you comment on this?
It is. I'm trying to find a quick way to explain it. Maybe the version, there are different variations of it. There's device independent, but there's also some measurement device independent. So device independent, I think it's a broader class of things that you can look at. But let's say you want your quantum key distribution to be independent of your measurement device. The measurement device, you can purchase it from the Eve, who's trying to extract information from your experiment. So you can, and the way that usually works, you can also think about it as a time-reversed entanglement distribution idea, where you try to sort of establish entanglement instead of sharing entanglement. What you do is that you start from independent sources and you interfere them in the middle. So your detection device is in the middle, held by a party that you don't trust. This allows you to, well, just relying on the correlations you expect from quantum physics of the problem, you can find out when this person in the middle is giving you false results or manufactured results. So that's how I generally describe it. So it is still a topic, but everything in quantum communication is that how paranoid you are. So you can have different conditions, different layers of security, depending on how paranoid you are. So for example, if you don't trust QKD at all, then you can go to protocols which relies on entanglement directly. So it means that it's more difficult to implement, but you can rely more strongly on the results. So all of these different flavors, variations, all depends on different levels of paranoia.
Okay, thanks. I think that's all the questions from the chat. Crispin or Hugo, do you have any questions?
A very interesting talk. Thanks very much.
Thank you.